Hi everyone, we're going to have a look at some concentration and titration calculations. Hopefully you're already familiar with calculating molar concentrations using the equation moles is equal to concentration multiplied by the volume. But ensuring that you have the concentration in mole per decimeter cubed and the volume in decimeter cubed. When we look at titration calculations, it's important that you're happy using this calculation. Titration calculations follow a supposed or a real experiment and allow us to calculate the concentration of a solution. For this, you need another solution which we need to know the concentration of, and this is often referred to as a standard solution. Let's have a look at an example question. So, 25 centimetre cubed of a 0.1 mole per decimetre cubed sodium hydroxide solution required 25 centimetre cubed of dilute hydrochloric acid for neutralisation. Calculate the concentration of hydrochloric acid. Here, it's important that we have the balance symbol equation. So let's start with that. We know we added sodium hydroxide to hydrochloric acid. We get sodium chloride solution and water. Here we see the equation balances without any need for balancing numbers. We're only actually going to look at the HCl and the NaOH, or the sodium hydroxide, because that's what we're told about and that's what we're asked about. We know we have 25 centimetre cubed of sodium hydroxide, so let's start there. And we know it has a concentration of 0.1 mole per decimetre cubed. From this we can work out the number of moles. Moles is equal to concentration times by the volume. So I take concentration, 0.1, multiplied by 25, but this is in centimetre cubed and we know it has to be in decimetre cubed. So 25 divided by 1000, and this gives me 0.0025 moles. As we can see from the balanced equation, the HCl and the NaOH react 1 to 1. So if we have 0.025 moles of NaOH, we must also have 0.0025 moles of HCl. We were told in the question that 23.5 centimetre cubed was needed for complete neutralisation. From this, we can work out the concentration by rearranging this equation. Concentration is going to be equal to moles divided by the volume. Here, we know the number of moles, 0.025, and we know the volume, 23.5. But again, remembering that I must convert this into decimetre cubed. So 23.5 over 1000. This gives us an answer of 0.106 mole per decimetre cubed. And that's our final answer, our concentration in mole per decimetre cubed. Hopefully you could follow this one. It's not too tricky. They can get a little bit more complicated. Let's have a look at this one, which is slightly more wordy. Okay. 25 centimetre cubed of an iron 2 sulphate solution of concentration 0.3 mole per decimetre cubed was acidified with an equal volume of dilute sulphuric acid, an excess, and then titrated with potassium manganate solution to reach the end point of the titration. 40 centimetre cubed of the potassium manganate solution was required. Find the concentration of the potassium manganate solution in mole per decimetre cubed. And we're given this equation. This one is actually a redox titration, but even if you have no idea what that means, you should still be able to have a go at the calculation. We're given this ionic equation, which looks a bit different from our normal balanced equation, but actually doesn't make any difference to our calculation. We see that the aim here is to calculate the concentration of the potassium manganate solution. And here we see the manganate ion in our ionic equation. We are told about the iron 2 sulphate solution, and we see the iron 2 plus here. We are also told here about the iron sulphate solution being acidified. This refers to the H plus being added here, but for the purpose of our calculation we can ignore this. So the first thing to do is look at the information we are given. We are told that 25 centimetre cubed of the iron 2 sulphate solution with a concentration of 0.3 mole per decimetre cubed was used. From this we can calculate the number of moles. Moles is equal to concentration multiplied by volume, so 0.3 multiplied by 25, remembering to divide this by 1,000. This gives us 0.0075 moles. If we now look at the balanced equation, we can see that the ratio of MnO4 to Fe2 plus is actually 1 to 5. This means that every 1 mole of manganate reacts with 5 moles of Fe2 plus. As we have calculated the moles of Fe2 plus, in order to calculate the necessary moles of manganate, you must divide this value by 5. This gives us 0.0015 moles of our manganate ion. We can now use this value along with the volume, which was given in the question of 40 centimetre cubed, in order to calculate the concentration. We know from rearranging our equation that concentration is equal to moles divided by volume, moles 0.0015 divided by our volume, which is 40 over 1,000, and this gives us a concentration of 0.0375 mole per decimetre cubed. So not as horrible as it looked at all. Hopefully now you can have a go at some of these yourself.